let's do an exercise working with some people around you. I want you to familiarize yourself again with some bond line condensed common structures. So I'm going to put up some bond line structures, want you to copy them down. Some condensed structures, want you to copy them down. And work with the people around you to figure out what the other version would be.
Draw the ring, or do you want to just write pH?
Yeah, that's condensed, so make sure you're drawing its bond line. Draw the ring.
How's it coming along over here?
What did I miss?
We're filling in these. Okay, good start on your own, no matter how far you got. Now turn to your neighbors. Which ones came easily, which ones did not? Did you have any that were different?
What am I doing?
One where he gave us the bond line right at the end. The one where he gave us the event.
Oh.
Easy. Where'd you go? Nice. It's a long way.
It's right there. You can see it. You could throw a stone.
I could throw a stone faster than I can scale the building, yeah.
So that's the IU
I can throw a stone a lot farther than I can jump.
How does that negate my point?
Did you have one on your way over too?
Yeah. John, I appreciate you.
Because there's not two. And Esther needs two.
Esther.
I'll let you know.
Oh, that'd be really ideal.
Oh, I'm sorry, the MEC parentheses BI.
Oh, interesting.
Because, yeah.
No, there's a couple of ways you could do it. I
Yeah.
feel like the way you're probably most familiar with seeing in class would be CH3, CHBr,
So that is the same exact thing as
and just write that in as a like that.
That is true.
Another way you could do it is
Oh.
like T, butoxide, which actually doesn't have the T in it. TBUO. This is a sec butyl.
yeah, it's the same
You
thing.
could
I
call
just
this
didn't my hydrogen now.
SBUO. Sec butyl.
Yeah,
I'll go over them.
Doesn't forget them.
What does the O mean in parentheses?
Oxygen.
No, I just. What do the parentheses mean?
It just means that it's not in the chain, it's a branch off. So,
Methyl.
With the chicken foot.
Oh.
So it could be
Well, if it would give you a different C amount, then it might be useful. Yeah. All right. So, pH. It's not even necessarily condensed. We could also have written it as C6H5CHO, and that's what the pH is giving us. What is that pH? Yeah, that's benzene or a phenyl group. So our bond line structure would have these alternating double lines. Our second unit, what we're moving into next week, we're going to deal a lot with aromatic rings. So we're going to look at different ways that we can draw them. CHO, aldehyde, better written as CHO than COH. COH makes you think of an alcohol, OH. CHO reminds you the carbon is bonded to the H. And then it's not another bond from H to O, but the oxygen is also bonded to the carbon. So we get this aldehyde, which Jamie wanted to ask, could we keep the pH in there? And you can. That would be another way of doing it. This is a little bit of like hybrid condensed bond line. Depends on how you want to classify condensed. All right, this one has a few options. You could call the condensed structure CH3, CH, CH2, CH3, and then off of the CH carbon, draw in the bromine. Or, I think it'd be fair to say that this could be CH3, CHBr, CH2, CH3. But you can also recognize that this is a butyl group attached at that secondary carbon. So it's attached to a secondary carbon with methyl and ethyl. So you can also call this sec-butyl bromide. Now, you probably are not used to seeing that SBU for sec-butyl, secondary carbon attachment, because you're more commonly seeing tert-butyl, TBU. It works all the same, although less common. Another way that you could abbreviate this tert-butyl group, don't use its IUPAC condensed name, but call it CH3-3CO-. Condensing those three methyl groups into one parentheses group. And then lastly, this one. So a couple of questions. Is this an ester? No. Why is it not an ester? Ester needs two oxygens. There's only one here. What are the parentheses doing then? The parentheses are trying to do something similar to what you see with the aldehyde. It's trying to say this oxygen is not an ether. It has more special bonding going on. The parentheses is telling you about a carbonyl with a methyl group on one side of that carbon and an ethyl group on the other. And we don't need to use Me and Et. Another way that we could use condensed structure here, CH3, CO, CH2, CH3. First, Killian?
Can you swap the methyl with hydrogen?
I mean, you could do anything
In the
your heart
condensed form,
desires.
if you swap it with hydrogen, does it make sense?
It would just become an aldehyde, and it would be more commonly written as CHO.
Okay.
Like you'd maybe say CHO, CH2, CH3.
What is that distinction with the O in the parentheses?
So that you don't get it confused for being an ether group between these. I don't want you to have no parentheses and think, oh, it's an ether to this and ether to that.
Just as it stands alone.
It just helps it stand out more. And it's not my format, to be fair, but I have seen it on like MCAT study guide questions. They will report a condensed molecular structure like this. I just want you to be familiar with it.
So if you did MECBR, ET, you lose a hydrogen in the one. Why wouldn't you want to do it on carbon parentheses?
Hang on. MECBR.
C parentheses BR.
Ah, right. Well, it doesn't indicate the hydrogen that's there.
Yeah, that's what I realized you missed. But what if you did like HCBR?
So MECHBR ET. I think it just looks clunky is all.
Yeah.
And honestly, that is one thing about reporting structures. Oftentimes, we're just doing our best to report in a way that's meaningful. Now, I told you guys about the PLOs on Canvas, right? Those are required, bonus, not graded. I mean graded, but you don't lose points for getting things wrong. You only get bonus points for doing things right. And they are written not by myself, but by the course lead for organic chemistry. And therefore, they look a little bit differently. You'll notice that a lot of those molecules have a lot of condensed molecular structure, which I don't really lean into much, but I do want you to be aware that it's a way to represent a compound.
Are we allowed to turn that in multiple times, or is it just like one trial?
That's a good question. I am going to have it be just a one-time turn-in because it's not a graded assignment, so I don't necessarily want to just provide feedback on it, because the feedback I do give you on written work, on unit tests, it's meant to prepare you for the midterm and the final. And the PLOs, while beneficial, I can't give you feedback that prepares you for the midterm and the final with it. Yeah. So I will go through and tell you what you got points for. And because of that, if you wanted to come to office hours or send me an email and say, I think I made corrections, could you check it again? I'll do that, but I wouldn't worry too much about it. Yeah?
I want bonus points, so that's where I was.
I get it, yeah.
I would like the most amount of bonus points.
I would say the reason most people don't get those bonus points is because they just don't do all of the problems. So then they just lose points for that. Good question. There is something that I wanted to draw your attention to on our modules page. If you come down to the Unit 1 module, which we are wrapping up this week, and open up this document, Unit 1, Learning Objectives. I took some time over the weekend to try and put into words the action terms that I want you to be able to do at the end of this. So they're all phrased as students will be able to, and then they've got action verbs: interpret, describe, use, predict, apply, predict. I think there's another interpret when it comes to spectroscopy at the bottom. What I've highlighted are all of those main ideas that we're tackling: bond line structures, formal charge, hybridization state, valence bond theory, MO theory. So we have a lot to cover still on our list, and I've named all of the reactions that I want you to be familiar with: radical halogenation of alkanes, of alkenes, elimination of alkyl halides with various things, elimination of alcohols, substitution of alkyl halides, substitution and transformations of alcohols, alkene addition reactions, by far the longest part of the list, alkylation with alkynes, alkyne addition reactions, and you'll notice that there are 3 types of one of those alkyne additions. So if you feel like you can go through, can I borrow this quick? If you feel like you can go through this sheet that I posted on Canvas and correlate them with this and find the reactions that are on here that are not reported on here, then I think you're in a good place when it comes to reactions. You're familiar with the names, you're familiar with what they look like. And then spectroscopy. I put the 3 main things that I want you to get out of them. Like with mass spec, distinguishing molecular ion from a daughter ion. With IR, correlating bonds to where their absorptions show up, the shape, the size, the frequency that it shows up at.
Without a table?
With a table. And then NMR, recognizing chemical shift, integration, and splitting pattern of a signal and how those signals build into a structure. So it looks like we've got a lot to do, because we do. So let's get into it. Any questions, though, before we begin? Yeah, actually, I do have another question. I want to make sure number 1 is really checked off well. So, by a raise of hands, can someone tell me how many compounds on this list have an atom with sp hybridization? No. Thank you. How many compounds have an atom with sp hybridization? I'm going to see if somebody else can answer. Are you saying the answer is 0? Anybody agree with Kayla that the answer is 0? Okay, none of you felt confident enough to say that, or were intimidated by me, or what was it? It's 0. None of them are sp hybridized. None of them have a triple bond, or 2 double bonds, or a single bond and double bond and a positive charge. I don't know if you guys have been going through that table of formal charges, but I want you to go back to them and label each example with its hybridization as well. Be able to predict hybridization. None of these are sp hybridized. Great. How many of these compounds have an atom with sp2 hybridization? 2 of them? Can you name them?
The one with the phenol group and the one with the carbonyl group.
Good. Those are the only 2 that have atoms with sp2 hybridization. That means they have a double bond somewhere. Or if it's a carbon, it maybe has a positive charge. And it's only got 3 electron regions, and it's trying to spread out as much as possible. When I talked to you guys about hybridization the other day, I gave you some lists underneath it. I said, sp hybridized makes 2 sigma bonds, 2 pi bonds. Maximum. It can make less than 2 sigma bonds. It could have 1 sigma, 2 pi, and a lone pair. Like with the alkyne anion. That's not 2 sigma bonds, it's just 1. Or it can make 2 sigma bonds, but only 1 pi if it has a positive charge. So those are maximum situations. And then especially when we start looking at heteroatoms, sp2 doesn't need to have 3 sigma and 1 pi. Lone pairs can take the place of a sigma bond. So I know that can feel confusing. In my Open 1 class, we did a similar exercise last night, and then I gave them structures to apply it to, and they were like, oh, it breaks the rules that literally are right there. And that's because it is malleable. That's a maximum situation.
Pyridine is sp2, right?
Let's look at pyridine. Sorry. 6-membered ring, 1 nitrogen atom. How many of those atoms are sp3 hybridized? None of them. All sp2. They are all involved in a pi bond, except for the hydrogens, which are s. They're not hybridized. I almost said s hybridized. The other thing I wanted to ask was, what charge is on that nitrogen?
It's a neutral one.
Good. We can never assume charge, right? Charge always has to be explicitly shown. So how many lone pairs does that nitrogen have then? 1. I drew it and then I erased it because I realized I wanted to test you. All right. How do you guys feel about learning objective 1? Interpreting bond line structures, formal charges, and hybridization states.
Can you distinguish the difference between formal charge and oxidation state?
I can. I don't often test on oxidation state. I've done it in the past. I got away from it for some reason. I've been meaning to get it back in, but there's just so many things to touch on. Oxidation state is really, really simple. Oxidation state is a comparative measure rather than formal charge, which is like an electronic measure. So for instance, take the carbon in methane, which is bonded to four hydrogens, and take the carbon in methane tetrol, which was reported as synthesized for the very first time this year. Doesn't look like that complicated of a molecule, but it's very hard to synthesize. The oxidation states are very different, despite their bonding patterns being very similar. Carbon is stealing electrons from all of those hydrogens. Each hydrogen gives carbon the electrons, so carbon gets a -4 oxidation state. Each hydrogen, in turn, gets a +1 oxidation state, and the sum of oxidation states of the molecule equals the charge of the molecule. What is the oxidation state of carbon in methane tetrol? +4. Each oxygen steals an electron from carbon, and so it gets a +4 oxidation state. What is the oxidation state of oxygen in each of those alcohols? Good guess. -4. Each one is -2. Because oxygen is not just stealing electrons from carbon. It's also stealing electrons from hydrogen. So from carbon, it's -4, a -1 at each of them. From hydrogen, it's another -4. Each oxygen is a -2 oxidation state. And then, of course, the hydrogens are a +1 oxidation state. All you're doing is looking at bonds to atoms that are more electronegative, giving them the electrons, taking on a positive oxidation state.
And if it's neutral, it'll add to 0?
Yeah, if it's bonded carbon to carbon, no change in oxidation state, 0.
Well, since we don't have a charge written on that molecule, we can assume oxidation states all add to 0.
Correct. The sum of all oxidation states should be 0.
There's no oxidation state of the molecule.
Correct. The molecule does not have an oxidation state. And then multiple bonds count multiple times. So, in acetone, can you give me the oxidation state of carbon? Raise your hand when you feel like you have it. And don't feel like you need to raise your hand because I'm going to call on you. Raise your hand when you feel like you have it. Yeah? 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 I see a nod, but not a hand. Good. Great. Good. Yeah?
I kind of zoned out. I didn't read the question. Sorry, I was reading what it was.
What's the oxidation state of the carbon in acetone? You have it? No? You have it? Jacob, you want to give it?
+2?
Jamie, do you agree?
I was torn between the left and right carbons taking away from it, so I was going to say +2 or +4.
Didn't you just say that if a bond to a similar atom, the difference in electronegativity, then it has 0? James, do you agree +2? The oxygen steals electrons in both bonds. The carbons aren't stealing electrons. So that carbon has an oxidation state of +2.
So is it fair to say that oxidation states deal very much with electronegativity?
Yes.
While formal charge does not. Formal
Yes.
charge is more based on valence
Yes.
and electron numbers.
Bonding pattern, I might say. Formal charge is based on the bonding pattern. How many bonds, how many non-bonds, how many lone pairs. Non-bonds.
So I was just doing some practice homework on that ABCs table that we did last week, and I found myself wandering into oxidation state territory without knowing it.
Sure.
So I just
So you
wanted
could, with that table, you could actually never figure out oxidation state because you don't know if those bonds we drew are going to more electronegative atoms that are putting a positive oxidation state or less electronegative atoms that are putting a negative oxidation state.
So you need the whole molecule to do anything intelligent.
You need the bonds, not necessarily an entire molecule, but you need a central atom and all of the bonds it's engaged in. You know what I mean?
The relative electronegativity.
Yeah. Take ibuprofen and zoom in on a central atom. You need to have each of the bonds full, but you don't need to know the rest of the molecule.
And the charge.
No, to figure out an atom's oxidation state, you wouldn't necessarily need to know the charge of the molecule. But all oxidation states in a molecule need to sum to the charge.
If you replace any hydrogen in that ketone with a fluorine, how does it change the partial charge of central carbon?
Partial charge or oxidation state?
Partial charge. Because right now it's partially positive from the oxygen.
Yep.
So how would you do one thing?
So the question is, how does the partial charge here change when any of these hydrogens are replaced by a fluorine? Well, that fluorine has a dipole that pulls away. This was already partial positive.
So it'll stay partial positive.
It's now going to increase its partial positive.
Are there 2.1s plus 2.1 oxidation state?
Nope. It's either more electronegative, less electronegative, or neither. All right, but we're not getting into it. But it's just too fun, and I do kind of want to get back into it because it is not hard. You just need to be familiar. All right. So we have covered interpret bond line structures, formal charge, and hybridization states. No more questions on them? We've covered describing bonds through valence bond theory and MO theory. Any more questions on those? Valence bond theory says overlap of these two orbitals, so you need to be able to determine hybridization state. MO theory says take these orbitals, put them high and put them low, make new orbitals that cover a molecule. And we've also talked about resonance and their contributions. Any questions on resonance still? How many factors to resonance contribution? 3 of them. And they are
Minimum charge.
minimum charge,
Maximum octet.
maximum octet, which predominantly applies to carbon. Oxygen and nitrogen all have maximum octets when they have negative or positive charges. Carbon loses an octet with a positive charge. And appropriate charge placement. That's the one that throws people off because they try to place the positive on carbon, but then they minimize octets by doing it. All right. Let's have a discussion about CARIO.
Oh, I remember what the O's were.
Good job, Jamie. What is it?
Orbital.
Orbital. It's one of the least applied.
So that's polarization, right?
I don't know about polarization. Maybe. I would say it's about electron repulsion. And normally they say look for the orbital shape to explain it. But
More S-like.
yeah, but I say it. And that could mean polarization. More S-like means more spherical. So more ability to disperse. Not all acronyms are the same. Some people go by CARIO because charge is just so intuitive, and there are also a lot of exceptions to charge. When I was in college, it was ARIO, A-E-R-I-O, and that distinguished the two facets of A. So we'll talk about what those two pieces are. First of all, charge, C, says more positive, more acidic, more negative, more basic. That's the gist of it, but it's not always true. So let's take, for example, a series of oxygen atoms. Let's take this metholium ion. No, I'm sorry. Methanolium. I forget how to make an alcohol a cation. Sorry. This is protonated methanol. The oxygen has taken on a hydrogen. And let's compare it to methanol, and let's compare it to methoxide. Cameron, how many lone pairs on the oxygen on the left? 1. Great. Luis, how many lone pairs on the oxygen on the right? The far right. Methoxide.
2.
Mm-hmm. Far right, methoxide.
3.
Good. All right. Which of these is the most acidic? Yeah, this protonated form. Which of them is least acidic? This is the least acidic because the only hydrogen available is bonded to a carbon, which we haven't actually even gotten to. Which of these is the most basic, most willing to accept a hydrogen? This one. Good. Now there are exceptions. For instance, if you take sulfuric acid and methanol, because they have the same charge, you may say that neither of them is a stronger acid than the other. But the products of this reaction, which is bisulfate and protonated methanol, the products are favored. The reaction prefers making protonated methanol. In fact, the pKa's of bisulfate and protonated methanol, this is still more acidic. And this is a weaker acid. So, charge, not always the best rule of thumb. A lot of exceptions to it because a lot of things change acidity. But when comparing in a generally simple environment, oh, these are all the same species, just at different stages of protonation, then it's really easy to tell them apart. Is that okay? All right. Atom breaks down into 2 pieces. The first is, let's say, atomic size. Larger atom, more acidic. This is only comparative within a family. Halogen family, the chalcone family, the nictone family, nictogen family. So that's nitrogen's family, oxygen's family, fluorine's family. So I like to actually give the example of oxygen. Let's look at ethanol versus ethane thiol. Which atom is larger, oxygen or sulfur? Sulfur is lower down. Bigger brother, sulfur is more acidic. We can also compare within a family. And this is electronegativity. which is to say more electronegative in a family, or excuse me, in a row, more acidic. Aminomethanol or hydroxyl methylamine. Carbon, nitrogen, and oxygen all available to donate their hydrogens. Which atom will donate its hydrogen the best?
Oxygen.
Why?
Most like negative.
It's the most electronegative in that family. So, can you guys remind me which way electronegativity trends?
To the right and to the middle.
Good. Electronegativity trends up and to the right on a periodic table. So recognize that electronegativity does not work when you're comparing a family. Acidity increases by decreasing electronegativity. In a family, acidity increases by size. But in a row, acidity trends by electronegativity. So in general, you can combine these and say that if you are comparing things diagonally down to the right of the periodic table, you can say it's going to be a stronger acid. So, for instance, carbon, CH, versus iodine, HI. Which is a stronger acid, CH or HI? HI has a pKa that's negative. It's very acidic. HCI doesn't exist. I think I had a conversation about this the other day, actually, with a Gen Chem student.
Really?
HCI, the electrons just don't work out. You can't. No, you can maybe.
It does work out,
Yeah.
but it just wouldn't.
Let's never talk about it again, though. It'd be like an alkyne to an iodine. All right. Working the other way feels a little bit weird, but you can probably make it work. So typically you're comparing in a row or in a family, but you can work diagonally because those two things are, they work together, they combine. I think going the other way from like fluorine down to the metalloids would be weird. You'd never see it, to be quite honest. You got a question on this?
Is the more electronegative more acidic because the more electronegative, the more you like a negative charge?
So there are a couple of ways to think about it. A more electronegative atom can hold that negative charge better. So its base is more stable, which means its equilibrium has less base reacting, more base there. Another way to think about it is that the bond is more highly polarized towards O. But that wouldn't quite explain why larger atoms are more acidic, right? So it can't be because of the polarizability of the bond, because this has a stronger dipole moment. But it's because this atom takes that negative charge and can disperse it over a larger area, weakening that negative charge. In terms of a magnet, this is big, and so its magnetic strength is decreased. A worse magnet, a worse base, makes it a better conjugate acid. R. Resonance. Renaissance. More resonance in the conjugate base means a better acid. More resonance in the conjugate acid means a better base. So this one is generally hard to sum up as easily. You can either say one of two things. What I just said, more resonance in the conjugate makes the original stronger. Or you can say, no, that's pretty much all you can say. So I'm going to put conjugate in this one, and it means you have to consider the product that is formed in order to understand the thing you're being asked about. Does that make sense? All of these so far, you're just looking at what you're being asked and determining how it ranks as an acid. Now, you have to think about what it forms to determine how it ranks as an acid. Increased resonance in conjugate increases acidity or basicity. Yes, sir?
Are there any exceptions to the atomic size one? The atom part?
Nope, not that I know of. Thank you for asking, but no exceptions that I know of. Cameron?
Did you say that increased resonance in the conjugate increases the acidity or basicity of the original?
That's right. So the thing you're being asked to rank, you have to imagine what it forms in order to rank it.
Basically, acids want to be bases, pretty much. They want to get rid of their hydrogen and become conjugate base.
I don't know if acids want to be bases,
They want to get rid of. They want to become their conjugate.
because
They're more stable.
a lot of things can donate a hydrogen. Carbon can donate a hydrogen. That makes it an acid. Can be a proton donor, but it doesn't want to be. It's not good at it. But where were you going with that?
I was just saying, if it's a stronger acid, it wants to get rid of its hydrogen more, and that will create a more stable conjugate base with the resonance. Think about stability of the resonance, because more resonance, more stability. Think like that.
Honestly, the way that I think about acid-base chemistry is, what does it form and how stable is that?
That's what I'm trying to say.
Because acid-base reactions are in equilibrium, which means not that you create a certain amount of products and then you're done, but that your products are reacting to form the reactants at the same rate that your reactions are going to form the products. Dynamic equilibrium, meaning things are constantly changing, but it net stays the same. So something that makes a very stable base, like an oxygen that can hold a negative charge, or a sulfur that can disperse it, those things don't react readily, so they build up more. So your equilibrium is larger on that side.
And sulfur being bigger, that's isn't that going down into orbital almost?
No, it's polarizability, which is just atomic size.
Polarizability is atomic size.
Yeah. Yes.
The strength or weakness of an acid has more to do with its pKa than its pH.
Good question. pH and pKa are related, but they are not the same. pH is kind of a conditional setting, and pKa is an equilibrium constant. pH is not an equilibrium. Yeah?
So just because it has a lower pH doesn't necessarily mean it's a stronger acid.
Acids don't have a pH. The solution an acid is in has a pH. To your point, you can make a solution of acetic acid, which has a pKa around 5, that is more acidic than a solution of HCl, which has a pKa around -2. I'll show you in a minute. But you need to have just a very, very, very small amount of HCl in order to keep its pH above the pH of a solution of acetic acid. Because every molecule of HCl you put into that solution dissociates and creates an available H ion to contribute to the pH count. But for acetic acid, for every one molecule of acetic acid that gives away its proton to count towards pH, there are 10 to the 5 molecules, 100,000 molecules that hold on to their proton. So HCl, every molecule dissociates. Acetic acid, 1 in 100,000 molecules dissociates. So you can control the pH with anything. But it's very hard to, because with HCl, it's kind of like an all or nothing. And with weak acids, it's not all or nothing. It's only partial. So pH and pKa, not exactly the same. Actually, if you want to relate them, the equation that you're looking for, do you guys remember? What is it? There you go. The, what's that magician's name? The Hasselhoff equation is what it reminds me of. The Henderson-Hasselbalch equation, which relates the pKa of an acid to the pH of its solution with a ratio of the concentration that you put in. So it's not exactly the same, unless the ratio is, there is a way, 1. Right. If the ratio of acid to conjugate base is 1, the log of 1 is 0, and the pH is equal to the pKa. So if you had an equal ratio of HCl and Cl minus, then your pH would be equal to the pKa of HCl. And the sorry, -2. Let's actually see if I'm right about that though. I've got it on this functional groups and pKa table. HCl, oh, -7. And different sources will vary on pKa values, by the way, but these were the most consistent numbers I could find. And -7 is an incredibly acidic pH. I know most people think the pH scale goes from 0 to 14, but it doesn't. It can go beyond that.
So is it fair to say that pKa is the potential to change pH?
Yeah.
The lower it is, the less of it you need to affect pH.
No. Here's what I would say. pKa is how well an acid does just that, is an acid. How well an acid gives away a hydrogen. pKa is a ratio. Well, first of all, it's the log of a ratio, opposite the log of a ratio, of the concentration of hydrogen ion and conjugate base to the concentration of the acid. If there's a lot of this, meaning the acid has done its job well, then this number is very, very large, and opposite the log of it is negative. If the acid has not done a very good job, and this is very, very large, the number is less than 1, and opposite the log of it is very positive. So pKa is how well does that acid be an acid?
Would you say that's a lagging measure almost? Like something that you're measuring how well an acid has performed its job being an acid after the fact? Or is that just semantics?
Or how well it will,
Okay.
or how well it's known to do its job. pH is now putting it in the context of concentration. Do I have the teeniest, tiniest drop of an acid dispersed in 2 liters of solution? Or do I have 1 drop of water on 10 milliliters of this concentrated acid? Because pH, the only difference there is it's the opposite the log of the hydrogen ion concentration, which is this guy. But it's putting it into a bit more context. It looks like it's actually taking context away now that I put it on the board. But this is not in the context of a solution. This is in the context of a solution. What's physiological pH? Oh, it's not acidic? Oh.
Well, of your blood.
Blood.
It's 7.35,
Blood, yeah.
7.45.
It depends, I guess, what part of the physiology you want to talk about.
Yeah,
Doesn't your
so
blood have carbonic acid in
your
it?
stomach acid is too.
Sure. Okay, that's fair.
Yeah, so it all depends on where you're talking about in the body.
Okay, I thought the blood had carbonic acid.
It does, but it's always a lot of
there's a lot of buffer systems in place to keep it at
Yeah. Yeah. Okay. Well, I'm not a biochemist for a very good reason. I remind myself of that often. Yes, sir.
H plus and A minus the same.
H plus and A minus are not the same. H plus is the proton that has been donated. A minus is the conjugate base.
Shouldn't it be the same concentration?
Oh, I'm sorry. I thought you were asking if they were the same species.
Okay.
They can be the same concentration, yes. Okay, back to our example about resonance. I wanted to show you guys the lab reaction you just did last week, which was the synthesis of methyl orange. The procedure tells you that this compound is generated first. And then it says it rapidly becomes this. Well, notice that these are just structural isomers. There's a hydrogen on this nitrogen at the bottom of this methyl orange. And now that hydrogen is on this nitrogen. These two conjugate acids are not the same. This is a weaker conjugate acid. This is a stronger conjugate acid, which means taking away this H+, this is a weaker base, and taking away this H+, this is a stronger base. Why? Because this compound as a base can delocalize its positive charge. So now when this cation forms in equilibrium, it's stabilized and it's less likely to go backwards. But the other one has no resonance stabilization. So increased resonance in the conjugate increases either acidity or basicity. Here's the examples that I like to give. Killian knows this one. Acetic acid versus methanol. Where acetic acid becomes acetate, which has resonance between the two oxygens. This is a better acid because it has more resonance in the conjugate base. Methanol just becomes methoxide, which cannot delocalize that negative charge. And in a similar way, sorry, Killian, looking at these as bases. Actually, I think I want to just pick just acetate. Acetate has two oxygens that can act as bases. One of them has resonance, and the other does not have resonance. Sorry, I know that is a little cluttered in there. The oxygen on top, when it acts as a base, delocalizes the positive charge, which stabilizes the conjugate acid, compared to the oxygen on the bottom, which, when acts as a base, does not stabilize the positive charge by resonance, is a stronger acid. So if I were to give you acetic acid and say, which oxygen is more likely to act as a base, you can predict the two possible conjugate acids and look for resonance. More resonance means that original oxygen is a better base. This is a better base. It stabilizes the conjugate acid better, right? What does a positive group want to do? It wants to donate. Positive charge means it's more acidic. So how can I minimize its desire to donate that proton? Spread out that positive charge. Don't localize it in one spot. Spread it out so that two atoms are half positive. I think you had a question, Killian?
Top right versus bottom right. So that oxygen on the top right, can it form 4 bonds? It already has 3. And is
No,
it,
oxygen really won't form 2 bonds. Or 4 bonds, sorry.
so that's why. If it could the resonance be equal?
I'm not quite sure. No. No, this won't take on 2 bonds. I did forget something though. Charge. Don't have my positive charge. You know, one time in grad school, I think maybe the first time I made a mistake on the board, which happened a lot, first of many, a student pointed it out. My students didn't like me in grad school because they could tell I was dumb. And they were like, that's not what you said, but just what you drew something different. And I don't know that everybody heard them, and I was like, oh, you're right, and I just fixed it. And then I was like, nobody knows that I'm stupid. And then somebody was like, if you make a mistake in front of the class, you should be the one to point it out and wait for every student to look and notice. Because if you just change it quickly, people have already copied it down. They're not going to pinpoint that one little spot where you made a change. So you'll notice that this semester, when you point out mistakes to me, I will actually draw everybody's attention to it to try and make sure that you all change it because it's necessary. You should all see it. All right, we're on our last 2 topics of CARIO, which is induction. Induction is just another way of saying push and pull of electrons. So more electronegative atoms, more acidic. It begs to argue then that if you have less electronegative atoms, you actually have a more basic compound. Now, unfortunately, all of the factors of CARIO are compounding, which is why something like bisulfate is actually still a better acid than protonated methanol. And that's because bisulfate has a lot of induction and it has a lot of resonance. And its orbitals are different than methanol. So there's no way to say, look for this first, then this, then this, then this. A lot of times when I have questions on this, I'm tackling different concepts entirely. So that you don't have to say, well, how do these factors compound, add together, subtract? That can be really challenging. A couple of examples that are really common is comparing acetic acid with trifluoroacetic acid. Trifluoroacetic acid has more electronegative atoms, and those are pulling on electrons. So 2 ways to think about this. They're pulling on electrons in such a way that oxygen wants to give up its bond to hydrogen so it can satisfy those fluorines more. But again, I like to think about the conjugate base that forms. If this oxygen takes on a negative charge, fluorine is happy to hold on to that negative charge. Makes a very bad conjugate base, which in turn makes a very good acid. Whereas this oxygen doesn't really have anything that wants it. In fact, it's got these groups pushing back on it. And so we can expand that to this other idea. Let's look at methoxide and tert butoxide. Can you tell me which of those is a better base?
Methoxide,
You want to tell me why?
just because there's less carbons, it has the equal amount of
Well, this is saying the more less electronegative you have, the better the base. Maybe I should have put more PN for more, oh no, more EP for more electropositive.
Who says?
What do you think is less electronegative? 3 hydrogens with 1 carbon or 9 hydrogens with 3 carbons?
Becomes less electronegative.
Yeah.
3 on the left.
Okay. So you think adding, just multiplying it by 3 contributes to electronegativity? I mean, it's kind of fair. So maybe it would be better if I say it as more electropositive. What's the opposite of electronegative? Electropositive. Electronegative is pulling on electrons. Electropositive is letting go of electrons. So if you have more electropositive groups, then you have a better base. This only has 4 electropositive groups. Really, the 3 hydrogens. Whereas this has 3 methyl groups, 3 times as much electropositive groups, 3 times as much basic. No, it's not a direct 3 and 3, but more basic. So this was a better acid because it has a weaker conjugate base. This is actually a better base.
Does the 3, or sorry, does the 4 carbons being big and more area to, I guess, hold more area, more charge per molecule area? Is that what's going on here? The bigger molecule has more area to distribute a charge?
It can't distribute its charge. There's no resonance. Don't distribute. It's not a different atom with a larger orbital. Don't distribute.
Why is it more basic?
It's got more push. It's got more of an electron cloud sitting behind this negative charge that says, look, we already want to give you our electrons. Yeah, there's a few guys here that want to give you electrons. But there's a horde of atoms here that are willing to give oxygen those electrons. Why would oxygen need to hold on to that negative charge? Oxygen will share it, which is the definition of being a base.
What happens to the arrow if you give oxygen the hydrogen?
But then you start looking over here, and you still have the same idea. If this becomes protonated methanol, and this becomes protonated tert-butanol, this is still a better base. This will turn into protonated tert-butanol faster than this turns into protonated methanol. This is always a better base than this because it has more electropositive groups. It's that push and pull of electrons from the surrounding electron cloud.
The electron positive is the push side of that.
That's true, yep. And electronegative is the pull side.
There's more for the negative to pull.
Sorry?
There's more for the negative to pull on the tert-butox side, on the far right, because there's more electropositive. Like the ratio of electropositive to electronegative is a greater difference.
I would say there's not much electronegative here because this is what we are referencing as our base. So we won't think about its electronegativity or electropositivity. So this is pushing on that oxygen, which makes it want to share its electrons more. Whereas this is pulling away from that oxygen. So if it has a negative charge, it stabilizes it. Destabilizes the negative charge, makes it a better base. Stabilizes the negative charge, makes it a better acid. All right, we've got one last concept, and I'll give you guys a quick break. That is orbital, and this is probably the easiest one because really, we're only going to apply it to carbon. The idea is more S character, more acidic. So in a small molecule, this is called Pent 3-ene 1-ine. It's got 5 carbons. There's an alkene at position 3, an alkyne at position 1. Pent 3-ene 1-ine. I'll write it down. Which of the drawn out hydrogens is the most acidic? Which of these is the best acid? Relinquishes its hydrogen first. On the left? Why would it have the most S character? sp hybridized. 50% of its orbital is S versus sp2 and the least acidic sp3. If you look at pKa's, you're looking at something like 25, 35, and 50s to 60s. So 10 orders of magnitude between some of these groups, which is 10 to the 10 times more acidic. That's this is 10 billion times more acidic on the left, and then this is another 10 billion times more acidic. Okay. It's best applied to carbons. I think you can make the same rationale about nitrogens and oxygens. It's just less common that you see it done. Why? Because this is organic chemistry. I will say, if you want an organic base, nitrogen is often used because it is a good base, but that's not what you're asking. Why does orbital make this impact? The way that I think about it is, if you put a lone pair here, it is 180 degrees away from electron repulsion with another lone pair, or another pair of electrons. Whereas a lone pair on this carbon is 109 degrees away from electron repulsion. This experiences the most electron repulsion. This experiences the least electron repulsion. That makes it more stable as a base. That makes this less stable as a base. That's how I think of it. There might be other reasons, but to me, that checks all the boxes. Let's take 5.
Wouldn't electrons pushing make it more stable because
No.
they're right next to
Electrons pushing on electrons make electrons want to go do things. Make electrons want to go away.
The electrons are in a mosh pit. They're always banging against each other.
Yeah.
So they're only stable in their shell.
Bonding electrons are more stable than lone pair electrons, often, not always. And I say that because lone pairs experience more repulsion with other types of electrons than any other type of electron.
Oh. Or.
Telemarketers.
Oh, you just said 2 different things. You said repulsive and electronegative, which I think means that if they're electrons, you're going to be pulling them in. No, you get a lot of telemarketers?
My number got sold to real businesses in Indiana, where I'm from. And so I just get these real people reaching out to me all day long. Like, they're completely real companies. They're not like telemarketers or anything. They're like, we do roofs. We do pest control.
Oh.
And it's like a real person.
Oh, no.
Yep.
That's
So
terrible.
It just makes me feel bad because I can't even just like go, like, you can't be rude on the phone. This is a real person.
Yep.
It's a poor little intern, 18-year-old kid who's calling me. He has a long list.
Well, I will be honest, I don't answer the phone unless I know the number.
They text too.
Yeah, that sucks. Well, I think on iPhone you can say, like, delete and report junk, and it might block it.
I do it every time, and I block them. It's just there's so many.
Dang.
At this point, I get at least like 3 to 5 a day.
That's wild. No way.
Yeah.
You can't just say take me off your list.
I do it to every single one who actually calls because they'll do it.
Oh, good.
But there's so many of them.
Yeah. And maybe they're being resold.
I think they are getting resold,
my phone plan is my family's, and it's under my uncle's name. And I just had a colleague try to exchange contacts by bumping our phones together, and it created a contact for me on her phone, but it didn't save my phone number. So then I called her because her contact did give me a phone number. I called her so that it would be saved in her phone, and it came up on caller ID as my uncle's name. And she's like, have you been lying to me about what your name is?
Could you imagine?
And I was like, no, but I didn't know it would show up like that. That's so strange. My phone number was actually my home phone number, the landline, growing up. So I know my phone number by heart because I had to give it to people when I was a kid before cell phones were big.
You still have your landline?
I don't have a landline. The landline phone number is my cell phone.
Your mom and pop.
They don't have a landline.
They checked it. It's gone.
That phone number is my phone.
It was kind of lucky you just carried around a landline everywhere.
You know, actually, my brother got that for Christmas. It's like an aux port that plugs into what looks like a landline.
Oh, that's
So you can answer your phone from like a corded phone. So I actually get a lot of people back from Wisconsin that look up my parents in the phone book and try to call my parents. Hi, this is Florence calling for Tim, but is Bob there? I don't know how to reach him.
the accent with that too. You're good at that.
Use the accent.
And I again, like I don't answer them because a lot of calls from Wisconsin are also fake. They're also scams. So I can't tell if it's a scam number from Wisconsin or a customer from Wisconsin trying to get my dad.
It's always your same area code.
Yeah.
We get you.
And so like the town I grew up in all had the same number, like 477. And so when I see a number that is 920-477, I'm like, wow, this would be a really surprising scam. But I still don't want to pick up the phone and have them go, who's John? Nah, I'm trying to talk to Bob.
And then they can't hear you on the other end.
Yeah.
The whole
Yeah,
time.
and I'm like, you need to call the company. Stop calling my dad directly. That's so weird. This isn't 1990 anymore, okay?
Oh man.
Leave a
I'm
message.
And I get people just calling me like 24/7, and I always feel bad. 'Cause I'm like, hey guys, I got it. It's 9 p.m. I don't care that you're applying for jobs in the evening or 2 a.m. That's what
Yeah,
happen.
yeah.
My phone does ring. We can leave it alone.
Crazy.
I'm 100% convinced someone's just like using my phone number and for just like anything. But they'll just get like text. It's one person named Tiffany. I have no one in my family named Tiffany. Like my phone number comes from my mom, which came from my dad, who started like kind of started a whole family plan.
Yeah.
You should
And they'll reach out, hey,
Like, he's
Tiffany.
like, hey Tiffany, we need you to check in with this, or hey, call us back at this doctor appointment. I'm like, I'm not Tiffany. I
You should answer
totally.
the phone as Tiffany though. How funny. It's like, yeah, it's Tiffany.
Yeah, I feel bad because I feel like somebody said like I'll get like some voice messages like, hey Tiffany, this is Drew. Call us back immediately. I'm like,
So
I
this is only
can't do
better.
anything.
It's easier to form
I hope
3
Tiffany's
bonds.
okay.
This is only better
Drama around Tiffany.
This is only
because
Yeah.
it stabilizes the charge.
But
When I do
because
keep
it's
getting like
easy to
random
form
texts,
3 bonds here,
it's
1, 2,
like
3,
they may be
1, 2,
mistaken.
3,
It's like
versus,
probably like one number off
1,
or
2,
my
3,
phone
4
number, and they just
here.
This forms 3 bonds.
completely
One,
mistaken.
two, three. To
Give
get
me a
resonance,
phone
you
number
need a
for
4th bond.
something.
No.
It's like, what?
No, you can't have resonance on that oxygen.
Why?
It can't accept any more electrons. For instance, why can't I
It
take
has
this?
it has 2 electrons right there.
Yeah, and why doesn't it go down here and push this up?
Because it's hard.
Well, it maximizes charges. You get a 2+ and a minus.
Because it's hard. So because it's so hard to form a fourth actual bond instead of leaving them as lone pairs. That's why this is better, because it's way easier for oxygen to form 3 bonds instead of 4.
All right, maybe I should have said more equal resonance forms in the conjugate base, more acidity and basicity. Because you're right, Killian, this could form another resonance structure, but it would not be an equal resonance structure.
So it would be way higher energy.
Way higher energy. Like maybe break universe physics.
Like way higher than this, or way higher than these. I know it's higher than both, so which one do you mean? Higher than this or
Higher than that.
the top one?
Yeah.
Okay.
I don't even know if he took his order.
Hey, John.
Scare me.
One of them
Is-
probably does.
Ignore the height.
Yeah.
That's just it. That's not what I'm asking.
He's so great.
So,
He's really
the
good.
same
He's
logic,
really good.
Which one would be? Which one would come off easier? This one or this
Jeff
one?
is awesome. The
Because
other
you got
guy,
a lone pair
I
here.
don't know his name.
Whoa.
Not
What?
as good.
It's not. For what it's not possible.
Tell me what are you asking?
Jeff did
What's a better
only
acid?
PA for like
The same logic in the
and then he
orbital one.
decided he wanted to go.
Yeah. Well, which one is more
He wanted
acidic?
to get his
This one or this one? Talking about
Because
this
he-
this atom.
Is the hydrogen here more acidic than the hydrogen here?
No, it's the hydrogen
He had to come back and work like, I don't know.
here.
That's what I just said.
To get his pension.
Oh, I thought you were talking about this hydrogen.
Yeah, like this is.
I'm
But
talking
you
about
said there was a lone pair there.
Yes, there is.
So there can't be two hydrogens.
Yeah.
Well, it goes right there.
Right. So you're asking, is this hydrogen more acidic or is this hydrogen? By the way, these have negative charges.
This is true.
So due to this having a 3 minus charge, this is going to be more acidic. Not to
The
mention,
charge is going to come
not to
out.
mention, this lone pair will now have some repulsion from additional lone pairs.
Justification for this one because there's electrons are like farther away,
Yeah.
so it's easier. So because there's electrons there, so this is easier. This is
No, I
easier.
think this would be more acidic, but I don't know if you can even prove that.
Orbital. How do I question this idea?
So first of all, charge, we know that more positive is more acidic.
That was my
Yeah.
issue, not that.
Then this doesn't actually have anything to do with orbital. That's sp3, that's sp3. This electron pair is not directly repelling against this electron pair because they're not on the same atom. And I'm saying that a lone pair in that orbital is 180 degrees away from the next bonding orbital. Then you're just looking at this. I think just make a better question.
Yes.
Sorry.
I don't know what that. Do not apologize for that. That was a good thing to say.
Don't stop asking questions. Just because I don't understand them or think they're relevant.
Okay. Question one.
Questions on CARIO? We're going to revisit CARIO throughout the semester when we talk about carboxylic acids and alcohols more. And we'll try to justify some of these things. We're also kind of going to revisit CARIO next week when we look at aromaticity. And it'll help us understand why certain structures are oddly acidic or oddly basic. All right. I think that the nomenclature that you learned in OChem 1 is relatively simple. And the nomenclature that we're going to learn in OChem 2 is relatively more complex. Here's how I like to break down nomenclature. Most names have a prefix. They have a root. That root may or may not have a locant that describes where the suffix falls. This is our very simplified basis. And to be fair, the prefix can have multiple components that have their own root, locant, and suffix. And this is not touching on multipliers when you have a suffix that appears multiple times. So you need to change di, tri, tetra, etc. So let's start real quick with root, because I think this is what you should be the most familiar with. Kayla, can you give me the root for 1 carbon chain? Meth. Killian, the root for 2, a 2 carbon chain.
F.
F. Jordan, the root for a 3 carbon chain. Pro. Roja, the root for a 4 carbon chain. Bute. Now, after those four, and to be fair, bute and prop and eth and meth, those are probably the most obscure ones. The rest should feel normal. Pent, hex, hept, oct, non. So I'm going to stop here at pent. And what if it's cyclic? What if you have a 3-membered ring, or a 4-membered ring, or a 5-membered ring, or a 6-membered ring? Add cyclo to the front. Cycloprop, cyclobute, cyclopent. I welcome you guys to fill those in if you want to, but I think you know it well enough. 2, let's look at the suffix. Suffix tells us not the carbon chain, but what?
How many?
Cameron?
What functional groups are there?
Yeah, predominantly, usually, one functional group in OCHEM 1, sometimes more than one functional group, up to 3 functional groups. And it's usually the most important functional group. Now, you guys that have had me before, you know that I talk about the difference between suffix and suffix stopper. Now, technically, textbooks don't talk about suffix stoppers. I might have invented it. I'm not sure. And I call it that because the suffixes are really based on hydrocarbon chains. So that means the suffix can be ane for alkene, ene. Did I what? I'm sorry. Ane for alkane. Did I say that?
Yeah.
No, I didn't. I said ane for alkene. Ane for alkane, ene for alkene, ine for alkyne. But the suffix can also combine ene and ein. So you get enine. Enine. I don't speak German, but I feel like I do when I say it. Suffix stoppers require a suffix. They require ane, ene, or ein to be there.
Like if you're doing double bound, triple bound nitrogen, you go E9?
No. Nitrogen?
Yeah.
No. Here. Alkene, alkyne, pent 3 ene ein.
Oh, the
Pent 3 ene 1 ein. Suffix stoppers require a suffix. They need an ane, ene, or ene ein. But then you drop the e and add on a new stopper. For instance, OL for the alcohol. And this is all we learned in OCHEM 1, which means this is all you're going to learn, or all you're going to see on the unit test review. But we're going to add more suffixes this semester. We're going to add own, al, oic acid, amine, amide, oil chloride, all sorts of fun stuff. So I'm going to leave it here, but I don't want you to think that you don't already know what comes after that, okay? So for example, this can become ane-all, like methanol. This can become ene-all. This can become ein-all. Or it can become ene-ein-all. And then you get multipliers, and you sometimes have to put the E back in. So earlier, I showed you guys methane tetrol. And you'll notice it doesn't just stopper ane, it actually keeps ane. And then puts tetrol with a multiplier. So it's not methane tetrol, it's methane tetrol. I'll be honest, I don't grade on the nitty-gritty stuff. I do hope that I can introduce you to the names enough that when you see a name, it will make sense to you. But I kind of doubt a lot of you will be out there naming compounds. And if you do, you should probably take a class dedicated to nomenclature. This class is not dedicated to nomenclature. Does that sound fair? Okay. Number 3, the suffix. No, sorry. Oh, you guys. I wish some of you would just be like, what? Louder, and rather than just in your head. Let's look at the locant.
I would be doing that all the time.
This simply describes where along the carbon chain a suffix appears if necessary. So there are some exceptions. Methanol, you don't need to say one methanol, there's only one carbon. Ethanol, you technically don't need to say ethane 1-all, because otherwise it would just be on the other carbon. What we can say is that we number to prioritize alcohol over the alkene or alkyne over the alkyl or the halide. Alkyl groups like methyl, ethyl, propyl, butyl coming off of a carbon chain, they have equal priority to fluoro, chloro, bromo, iodo. Alkenes and alkynes have equal priority in a name, unless there are both, in which case prioritize whichever one can have the lowest. Unless they both have the lowest, numbering from different directions, in which case prioritize alphabetically. When in doubt, prioritize alphabetically. But if there's an alcohol in the compound, number in such a way that it gets its lowest number. And then state it. Because you cannot assume, especially on a linear carbon chain, you cannot assume where these groups are going to fall. So, can we name these two compounds? I'm going to change that first one. Sorry. Just to give us some diversity of what we're seeing. Just made a triple bond. I'm sorry. See you guys erasing. I don't want to use a free eraser.
Free ones in the STEM Center.
There you go. There's free erasers in the STEM Center. I'll pick one up if I wear through yours. You got a name, Cameron?
I was distracted. My fault.
What does alkyl
Alkene
mean?
means carbon-carbon double bond.
Alkyl.
Oh, alkyl means carbon group.
Why alk?
I'm sorry, I'm giving you some examples, but I didn't really hit prefix. And then I gave you some that have a prefix. Prefix, like I said, is all of those substituents that can't be put into the root or the suffix stopper. So when you've got a branch coming off of your parent chain, it becomes a part of the prefix. And it needs to get its own locant to say where on the parent chain it goes. And it needs to get its own suffix, usually the suffix YL. So I'm just going to sum that up by saying prefix gets a locant plus its own root followed by YL. That's where we get methyl, ethyl, propyl, unless you get things like chloro, bromo, iodo. You don't say bromo, iodo, Yeah.
What about dyes and tris?
Multipliers, I think they'll kind of fit in. I kind of gave that example with the suffix. Tetral has 4 alcohols, so tetra is the multiplier. No, because what is 1 describing? Placement of the alcohol, which means it needs to go before the part of the name that describes the alcohol. Between ein and all. Notice it's like root locant suffix. It's actually kind of a privilege that IUPAC gives us to put the locant in front. It's not a guarantee.
So pro dash 2 dash in dash 1 dash old.
Yep. Yeah.
It's all of them.
Matt, how are you feeling on the first one?
I'm figuring it out right now.
Can you give me the root?
So this has the 3 carbons, so it should be the propyl.
Good. Not propyl.
Just propyl.
Yeah, the ul is a suffix that usually goes into the prefix. Good. So that first one has a root prop. And I know a lot of you are used to putting locants in front of the root. You can sometimes, but other times it needs to go in between the root and the suffix. What is the suffix for this compound? Connor, do you think you could give me the suffix, not necessarily the suffix and stopper?
Ein?
Yeah, because I'm gonna avoid ane because I have an alkyne. And then do you think you could give it to me with a stopper?
Einol.
Einol. Great. Luis, do you think that you can give me locants for ein and locants for all?
3 for ein and 1 for all.
One. I did not set that up, but I like the way it sounded. Prop 3 ein, 1 all. Cooper. Why? So here's carbon 1. We prioritize the alcohol. Where does the alkyne start? Carbon 2. Luis, do you agree?
Yeah.
What was your rationale between 3 instead of 2?
Oh, sorry.
You missed the oxygen carbon.
Did you count 1, 2, 3?
No, actually, yeah, it should be 2. My bad.
1, 2. That's where the alkyne starts. And we assume it goes through to the next one. 1, 2, 3. Great. Good teamwork, Cooper. Pro 2 ein, 1 all. Now, just to point it out, somebody showed me 1 prop 2 ein all. What does the 2 indicate? The position of alkyne or alcohol? It indicates what comes directly after it. So, the ein. So what is 1 describing then? It describes what comes directly after it, which is also the ein. So this name gives 2 locants for the same suffix. And that's why it can be tricky to ever put locants out front. IUPAC, who decides on naming conventions, they say locants should always go between the root and the suffix. They should never go out front, but they allow it. So, best name here looks like this. Such a small little molecule, such a big name.
What's wrong if you say 1-hydroxypropene?
So if you name the alcohol as a substituent rather than in the suffix, if you call it hydroxy instead of all, 1, you're not naming it the way that I'm teaching you to. I'm teaching you to make the alcohol a suffix stopper. There are reasons that you might want to make it a substituent. That's usually if you have a higher priority functional group that already claims the suffix stopper spot.
Higher than alcohol?
Yeah, like carboxylic acids and esters and amides and ketones.
We'll
and
learn about
halides.
that? Okay.
But if you did name that as a substituent, then you would number prioritizing the alkyne, and it would be 3-hydroxy 1-propyne, or prop-1-ine. All right, the second one. Cooper, can you give me the root for my second one? Cyclohex. Russ, can you give me the suffix and or suffix stopper?
Ene. Ene all.
Yeah, ene and all. And Jacob, can you give me locants for ene and locants for all?
2 for ene, 1 for all.
Right, keep doing that. Now, is it necessary to state the position of the alcohol in this compound?
No, not for knowing. Maybe for IUPAC.
IUPAC even agrees. On a ring, you get to start wherever you want at the highest priority functional group. So you have to start at the alcohol. You don't have a choice. Which means you don't actually have to say that the alcohol is at 1. It's not wrong to, but it's not required. Because of course you started there. With the carbon chain, you have to say it. Now I'm thinking back to this example I gave where it'd be unlikely that your alcohol comes off of the alkyne, but maybe not impossible. And the alcohol can't be on the second position because then you couldn't have an alkyne. So you maybe wouldn't even need to say 1-all here, but it just makes the most sense. So you can put in the 1-all, you don't have to. It's kind of weird. More redundancy, I think, is better. So having 1-all never hurt anybody. Maddie, do you think you could tell me the prefix for that molecule? What haven't we named yet? Good. 2 methyl groups, so multiplier, di, and they need a locant. Kayla, do you think that you could give me a locant for each methyl group? 2 methyl groups, di, 2 locants. You want to put one at 1 and one at 6? They're not attached to the same carbon? Oh, I'm sorry. Both at 6. So, locants.
I don't know what you're asking.
Yeah. What locants will I put here? Number, describing.
6.
There you go. Thank you. 6,6-dimethyl cyclohex 2-ene 1-all.
Why is it wrong to leave 1 is 6?
Because I don't know if you forgot that there was a second methyl group, or if that second methyl group was on a different carbon, and you forgot what carbon it was on.
So you
Tell
can,
me that they're both on carbon 6. Or tell me that one is on carbon 6 and one is on carbon 1, or 2, or 3.
you can have 3,6-dimethyl, so it's just
Sure, you could have
oh well.
3,6-dimethyl cyclohex 2-ene 1-all. Absolutely. Structural isomerism is a big deal, so we do need to get away from that with the naming.
So with the locant, we are going clockwise instead of counterclockwise.
Totally arbitrary.
But wouldn't that make the locant for the dimethyl 2?
Well, we want to prioritize alcohol. That's why we started with the alcohol being carbon 1.
Right.
Then we want to prioritize the alkene.
Okay, so the
Before we
alkene
prioritize.
outranks the dimethyl.
Correct. You see that list, right? Alcohol is greater than alkene is greater than alkyl. Alkyl is...
Okay, and the dimethyl is the alkyl.
That's right.
That's what I keep forgetting.
Good. ALK meaning functional group, carbon group, alkane, alkene, alkyne, alkyl. And there we've got the methyls. Those are the alkyl groups. Otherwise, we want to maximize the smallest number of locants at the first point of difference. So if we had numbered it the other way, we would have had 2,2-dimethyl cyclohex 5-ene 1-all. And that would be a lower set of locants, except that it breaks the rule of prioritizing certain groups. All right. So let's talk about all of the reactions. Man. No, but we do have a busy day for tomorrow.
Yeah.
Here is what I want to wrap up today with. It's some vocabulary that we've talked about before in OCHIM 1. Chiral versus achiral versus meso. There's certain trends that you can look for here. But why don't we put some examples? Is there a molecule on the board that is chiral? Yes, Killian, where?
Oh, it's that one carbon that goes to the alcohol.
Good. This is one chiral carbon. Do I know its chirality? Its handedness. Its absolute configuration.
Yeah.
No.
Oh.
Because I don't have any stereochemistry. I don't have a wedge or a dash. So this is, for those of you that had me in OCHIM 1, this is this. Left hand or right hand? Jacob's like, I saw you put your left hand up there. All right, Jacob. How about this? That's my right hand. It fits, right? Right. All right, now, what is it? Now it's my left hand because you have more information. Otherwise, it's not enough information. Not enough information to know whether it's R or S, but enough information to know that it's chiral. How do you know? 4 distinct groups. The oxygen, the quaternary carbon, the secondary carbon, or tertiary, depending on how you think of it, and the hydrogen. Is there a molecule on the board that is achiral? Jordan? The pro2-ine-all. Because there are no chiral carbons. No carbons bonded to 4 distinct groups. Is there a compound on the board that is meso?
No.
No, nothing tetral is also achiral. It's bonded to 4 identical groups, much like methanol, or methane. To be meso, you have to be bonded to, you must contain at least 2 chiral carbons, and those 2 chiral carbons must be symmetric to each other. So let's say cis 1,2-dimethyl cyclopentane. 2 chiral carbons with a plane of symmetry reflecting them. Trans 1,2-dimethyl cyclopentane becomes chiral. The relationships that we have with these molecules, enantiomers, diastereomers, and structural isomers, those are the most common ones. Tomorrow, we're going to kick off with looking at reactions, and we'll be putting up reactions from the same starting material to make enantiomers, diastereomers, and structural isomers. So we'll review some of that terminology then.
Great.
All right? Have a good night. Did I say tomorrow? But you know what I meant.
Yeah.
Next class. Go home and let your brain rest a little bit. Or go to the STEM Center and exercise it a little bit more before you go home and let it rest. Have a good night, guys. I'll see you on Thursday.
Johnny didn't get the chemistry of